Hello, everyone, and welcome back. So we are talking about 622 still, which is still implicit differentiation now. What does that mean? So recall from the last video, we looked at a few examples. And one of the examples we looked at, and it's the one we left off on, was the function 1 over y equals x. Now, if I asked you what's the derivative of this function, what's d dx of this function? Now, in the past, what you could do is you could solve for y first. Solve for y, then differentiate. So if you did that here, you would have 1 equals xy, which would imply you get y equals 1 over x. And then if you were to take the derivative of both sides, so what's d dx of y equals 1 over x, you would have that the derivative dy dx is going to equal, well, this is the same thing as x to the negative 1. So then with the derivatives, that would become negative x to the negative 2. Then I could write that as negative 1 over x squared. And that's great, and that works. However, sometimes you can't always solve for y. You can't always get y by itself. So there has to be another way, and that's where implicit differentiation came in. So implicit differentiation is the idea that you can still find the derivative because it's not always possible. It's not always possible to get y by itself. Y being the function where you can analyze it in terms of one variable. So this same problem is what I did last video, and I just want to do a review of it. So if I was to differentiate both sides with implicit differentiation, it says, hey, just take the derivative of the whole thing. We'll worry about it when it comes time. So what's the derivative? How is this changing relative to x, changing relatively small, right? The derivative is these infinitesimal small changes. So what you'd have here is this right here is the quotient rule. So you have to do the bottom times the derivative of the top, and the derivative of 1 is 0, minus the top times the derivative of the bottom. And what's the derivative of y with respect to x? We don't know, so then it's just going to be dy dx. What is the derivative of y with respect to x? We don't know. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Equals, and the derivative of x with respect to x is just 1. And then if we solve for dy dx, you would have negative dy dx is equal to y squared, in which then you would get dy dx equals negative y squared. In which you might be thinking, wait a second, Mr. Hine, these are two different things, and this is where I left off in the last video, and I contemplated to myself, do I tell you now? I said, the video is too long, we'll save it for this video. Are these the same thing? Well, remember, we could solve for y from up here. From 1 over y equals x, well, that would imply that y is going to equal 1 over x. So by that, if we plug that in, well, thus dy dx would be equal to negative 1 over x squared, which is negative 1 over x squared, which there you go. Are they the same thing? Yes, they are. Now, what does that mean? That means that you could talk about the derivative of this function, y equals 1 over x, or x equals 1 over y, and you could find its rate of change at any given moment, given its x or its y value. We could talk about rate of change given either of those values, and that's pretty important, and that's pretty amazing. So let's look at a few more, ones that we haven't seen. So let's look at a new example, and let's look at a function y cubed minus plus y minus 2x equals 5. And I don't quite know what this looks like graphically. It's not an easy function. So what's the derivative of this function? Could I solve for y? I don't know. That looks pretty complicated. So the power of implicit differentiation, where we just take the derivative of the entire thing. Okay, we just have to account for chain rule because we have something to the third power. So the derivative of something to the third is the derivative of the outside, leaving the inside alone, and that becomes a 2 due to the power rule, times the derivative of the inside. And what's the derivative of a function y with respect to x? Well, we don't know, so we just say dy dx. Plus the derivative of y with respect to x, is just dy dx, we don't know. And then the derivative minus the derivative of 2x with respect to x, which we can do, and that just becomes -2, equals 0. And then solving for dy dx, we could combine these two and factor out a 3y squared plus 1, and then that -2 will go to the side as just a 2. And therefore, we could say that dy dx, the derivative of this function with respect to x, how it's changing relative to x, making little changes, is given by 2 over 3y squared plus 1. And there you go. And just like that, we found the derivative of this function without needing to get y by itself first. Very good. Let's look at maybe one more example, and I'm going to go back to a circle because a circle is a nice one, so hopefully you got that. All right, let's look at one more example. So let's look at a circle. I don't even know. Let's just pick random numbers. X minus 3 squared plus y plus 2 squared equals 4. Keep the radius easy. Hopefully that makes my math easier. So let's draw this since we know what this is going to look like. So this is a circle centered at 3, 2, 3, -2. Okay. And it has a radius of 2. So that means here, 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 and here are the bounds of that circle. There you go. All right. So let's find the derivative of this function so we can find how this circle is changing at any given moment. All right. So we would just going to use implicit differentiation here with all our tools to take the derivative of this. So the first part would be the power rule. So it's going to be the derivative of the outside, leaving the inside alone, times the derivative of the inside, and the derivative of x minus 3 is just 1. Plus, we have the chain rule again, the derivative of the outside, leaving the inside alone, times the derivative of the inside. And the derivative of y plus 2 with respect to x was going to be dy dx. We don't know the derivative of y with respect to x, and the derivative of 2 is just 0. So we don't need to include that. Equals 0 because the derivative of 4 is 0. All right, so then if we solve for dy dx, we'll get here dy dx is going times 2y plus 4, if I multiply that out, is going to equal, and I'm going to have a 2x minus 6, so if I bring that over, it would have been a -2x plus 6, I believe, because that's 2x minus 6, -2x, and 6, good. And then divide by 2y plus 4 to both sides. So the derivative of this circle can be denoted by -2x plus 6 over 2y plus 4. And I can simplify that even farther and say -x plus 3 over y plus 2. And there's my derivative. Okay. Now, what if the question were to say, when is the slope of the tangent line undefined? What if it asked that question? How would you go about that? Now, undefined means that the slope is vertical. So this right here means the slope is vertical. Undefined slope, which also means that you have something over 0 because you can't divide by 0. So in this case, when is the slope undefined? Well, that's going to be the case when the denominator, y plus 2, equals 0, which implies that y would have to equal -2. Now, when is y -2? We can see on a graph that at -2, at y equals -2, there's 2 points here and at here, and which at both those points we could see that the rate of change is undefined, which is great. Now, if you wanted to find the exact point, just plug it back into the original problem. So we would have x minus 3 squared plus -2 plus 2 squared equals 4. Make sure my paper's showing. And you would get here x minus 3 squared equals 4, square root both sides. So you get plus or minus 2, and then add 3. So you would have plus or minus 2 plus 3, which gives you positive 2 plus 3 is 5. -2 plus 3 is 1. So we would say that the slope is undefined at 5 -2 and at 1 -2. And we can see from our picture that that aligns perfectly with what we believe. 1, 2, 3, 4, 5, -2, the slope is undefined, and at 1, -2, the slope is undefined. And now we have the algebra to back up what our visual eyes believe the answer to be. Very good. And then a follow-up question, if I was to go on this, is let's say, when is the slope of the tangent line? Equal to 0. Right? Well, if dy dx, if our derivative function is defined by -x plus 3 over y plus 2, well, when is this going to equal 0 implies that all we care about is when the numerator equals 0. When does -x plus 3 equal 0? Which is the case when x is equal to 3. And again, we can see from our circle that at x equals 3, you have 2 points here and here where the slope would be 0. At both those, you have that flat line. So that's aligns with what we believe. And if we were to solve for the exact points right away, because say this was astronomy and we're talking about orbital spaces, we want to know the exact location, which would be great. So then we would have x, well, not x, it would be 3 minus 3 squared plus y plus 2 squared equals 4, which that goes to 0. So then you'll have y plus 2 equals plus or minus 2, y equals plus or minus 2 minus 2, which would give you 0 and -4, which aligns exactly with what our picture is saying. Now, I want to go one step farther in this circle problem. Okay? So, one step farther in this. Let us start a new paper. And let me just bring up the points. So we were talking about x minus 3 squared plus y plus 2 squared equals 4. We found implicitly that dy dx is the function -x plus 3 over y plus 2. And visually, the circle is centered at 3, -2 with a radius of 2. Something like that. Not perfect, but gets the point across. Now, what if we wanted to find the second derivative? The derivative of the derivative, meaning how is the rate of change changing at any given moment? Okay? And what does that tell us about this picture? So there's 2 ways we could do it. We could continue from where we left off. So we could just do the derivative of dy dx equals -x plus 3 over y plus 2. Or you could, well, no, this is honestly the easiest way. The other way is you could do it from the beginning and just keep going where you don't actually solve for dy dx. Like, let me show you what I mean. Basically, you start back at the original problem and you take the derivative of this side one time and once, well, we'll work through it. Why not just show you? Okay, so let's work with this method over here. The derivative dx times dy dx. So what this creates is, notice this is just kind of a silly notation. D times d would be d squared y. And on bottom you have dx times dx, so they actually write it as dx squared. Now technically what that should be is like that, but the book never writes that. In fact, not many mathematicians do, which is, can be misunderstood, but that's the idea. So that's notation for the second derivative, and I hope you can see where that comes from, because d times d is d squared y, dx is dx squared. So how's the rate of change changing? It's going to equal, now let's go through it. So we have the quotient here, so it's the bottom times the derivative of the top, which the derivative with respect to x of -x plus 3 would be -1, minus the top times the derivative of the bottom, which is going to be dy dx, all over the bottom squared. Just cleaning this up a little bit, we'd have the second derivative is going to equal, I'm actually going to put this in front because this is going to make this positive. No, it's okay. It's going to be negative y plus 2 minus dy dx times switch that around and make it 3 minus x for purposes of easy to read. So we can see the second derivative relies on the first. Now this is not a good final answer. Your final answer should just have x's and y's in it, not relevant to its last rate of change. So from here, we're going to substitute in what we know dy dx to be. So then we would have d squared, second derivative, is equal to negative y plus 2 minus dy dx, and technically this is minus all of this, by the way, minus dy dx, which is negative x plus 3 over y plus 2 times, well, might as well keep that negative x plus 3, all over y plus 2 squared. Okay. Now just some algebra to worry about. D squared dy over dx squared is going to equal negative, let's write this as, let's multiply that out and write that as 2. No, because that would be negative 2. I like it as is then. Let's keep it as negative y plus 2. And over here, we would have minus, and this is going to become negative x plus 3. Those are in parentheses. Negative times a negative is going to be a positive. That would be x plus 3 squared over y plus 2, all over y plus 2 squared. Okay. Now, the way I like to work with this, and maybe know another way, is this is over 1. So when you're dividing by a fraction, you flip and multiply. So this is actually the same thing as 1 timesing by 1 over y plus 2 squared. So then by simplifying this, d squared dy over dx squared is going to be, if I do negative y plus 2 over times 1 over y plus 2 squared, I'm going to end up getting negative 1 over y plus 2 minus, and when I do this, I'm going to have negative x plus 3 squared over y plus 2 to the third. And then if I square both of these in order to have common denominators, what I would end up having is negative y plus 2 squared over y plus 2 to the third minus this, in which my final step, I can combine my fractions and have that the second derivative of this circle is given by negative y plus 2 squared minus x minus 3 squared over y plus 2 to the third. Now, a little neat fact is if I keep going, d squared dy dx squared, I could rewrite this. If I factor out a negative 1 on top, I could actually have up here, I could write this as x minus 3 squared plus y plus 2 squared all over y plus 2 to the third. In which case, take a look at this. The second derivative is going to become x minus 3 squared plus y plus 2 squared, where that was equal to 4. So all of that just becomes 4. So you have negative 4 over y plus 2 to the third. And there is our second derivative. And there you have it. Now, what's interesting about this is, what does this tell us? Like, we did all this math, well, does it tell us anything? What does it mean? All right. Well, let's see. When is this positive? Well, notice that this second derivative is positive when y plus 2 to the third is negative. Because if that's negative, a negative and a negative is a positive value. Now, when is y plus 2 to the third less than 0? Well, if we solve for this, it would be y, well, it's actually going to be, you have some number sense here. If y is a negative value greater than negative 2, or I guess you could say less than negative 2, then it will be, so if y is less than negative 2, because if you plug in negative 2 plus 2 is 0, which is 0, but then if you go smaller, say negative 3, you'll result in a negative, and a negative raised to an odd power is a negative. So you would say the second derivative is positive when y is less than negative 2. And we could even say that the second derivative is negative That's the notation for negative. When you would say y plus 2 to the third is greater than 0, because then a negative and a positive would result in a negative, and that's the case when y is greater than negative 2. Now, how does that relate to this circle? Take a look. Well, really quick, what does a second derivative mean? This means that it's concave up. So this graph is concave up when y is less than negative 2. I'll highlight that. And similarly, we just found out algebraically that this means that the graph is concave down when y is greater than negative 2. And take a look at our picture. If I bring the picture back into it. If I was to draw a line right here to represent y equals negative 2, well, notice that when we're smaller than negative 2, we are, in fact, concave up. And then when we are greater than negative 2, we are, in fact, concave down, just as algebraically we showed, which is really fascinating that now we can, all these visuals and all these things we see, we can back up with algebra now. So that's implicit differentiation, the idea that you can take the derivative without solving for y first, and when you get to taking the derivative of y, we would just say dy dx, because we don't know what the derivative of y with respect to x is, because that's what we're trying to do. So hopefully this makes sense a little bit. I hope when you try these problems yourself, you get better at it and it makes more and more sense to you. Come to office hours if you need any help or have any questions from me. All right, bye-bye, and good luck.